In this second video for section 3.2, Properties of Determinants, we're going to learn a new definition and then a little theorem that can sometimes make finding determinants a bit easier. We'll start with the definition. A square matrix is called singular if its determinant is 0. For now, we're only concerned with computing determinants, but later on in other sections, we're going to learn about why singular matrices are important. Let's work through an example now. Here I'm computing the determinant of a 3 by 3 matrix, so notice the vertical bar notation. And the important thing to notice about this particular matrix is that the third row has all zeros. So you might remember our strategy of doing cofactor expansion along the row with the most zeros, and that's what we're going to do here. We'll do a cofactor expansion along the third row. So when we do that, we get 0 times its cofactor, C31, plus 0 times its cofactor, C32, plus 0 times its cofactor, C33. So we don't actually need to compute any of these cofactors, because when we multiply each of them by 0, we know we're going to get 0. So overall, the determinant, doing next to no work, is 0. Let's try another slightly more complicated example. Here I'm again computing the determinant of a 3 by 3 matrix, but now there are no zeros. What I want to do is create as many zeros as I can. And one thing that you might notice is that the first column and the third column are proportional, meaning that if I multiply this column by 3, I actually get the third column. So what I want to do, using part 3 of the theorem that we learned in the last video, is to subtract 3 times column 1 from column 3. Normally when we do this kind of operation, we look at rows, but this theorem lets me do the same kind of computation with columns without changing the determinant. So what we get after we subtract 3 times row 1, or 3 times column 1 from column 3, is a new column of zeros. So what I want to do is my cofactor expansion along this column, and what we would get is 0 times its cofactor, plus 0 times its cofactor, plus another 0 times its cofactor. So overall, we get a 0 again, with only a small amount of work. So there is a little bit more than the last problem, but still, it's much easier than usual. So to conclude this video, we have a theorem that summarizes what we just learned in the two examples. I want to start with a square matrix called A, and A is singular if the elements of a row or column are 0, or 2 rows or columns are proportional. This first part is like the first example, where we had a row of zeros, and when we did a cofactor expansion along that row, we got a determinant of 0. So that means the matrix was singular. And then the second part is like the second example, where we saw that we could subtract or add columns to make a column of zeros when 2 columns are proportional. And again, we got 0 for the determinant.